So I'm Zhang. I'm an assistant professor in the Department of Geography at Texas A&M University. Welcome to our UCGS webinar, and thank you for your time. So I'm honored to introduce our speaker, Dr. Zhang from University of Albany, State University of New York. Dr. Zhang received a PhD degree in environmental health and a master's degree in statistics at the University of Michigan, and a master's degree and bachelor degree in environmental engineering in the Tsinghua and the Southeast University of China. So Dr. Zhang is an awardee of a state-funded Empire Innovation Program in year 2021. And his research interest focuses on characterizing climate-related exposures, reducing the human health effects associated with the disasters, and exploring the role of social and environmental stressors in relation to chronic diseases. So today, his topic is air pollution, extreme weather, and urban exposome, evolution of exposure science in the area of AI and precision health. So welcome, Dr. Zhang. Floor is yours.
Yes, thank you very much for introduction. Let me share my slides. So can you see my slides?
Yes.
Okay, great. Yeah. Thank you very much for introduction. It's my pleasure to have this opportunity to share my research with you today. So let's start from a doctor visit. So when we go to a doctor office, a doctor usually asks us how your symptoms feel like, how long you have had your symptoms. So what kind of medication you are taking now, your family medical history, and what kind of allergy do you have? So they never ask you, where you live and where you work. So this is a significant omission of social and environmental determinants around us. So this figure shows the contribution of social and environmental determinants to our health on a population basis. So, the first, I want to say, this figure doesn't account for genetics. So we know genetics, play a role in our health. So if we look at this figure, so basically, social and economic factors, medical care, and physical environment account for 40%, 20%, and 10% of our health. So, and also, actually, the 30% of our health is determined by our own choices and health behavior. For example, so what you eat, how active you are, and do you smoke and drink alcohol? So if we look at this part, so this figure, this part shows, in the real world, so we are being exposed to many social and environmental factors simultaneously. For example, air pollution, built environment, and a number of social determinants. So from a life course perspective, so our exposures, begins in the utero and continue throughout our lives. So, so the timing of exposure at a different life stage play a critical role in our health. For example, from the childhood, young adulthood, middle adulthood, and elderly. So basically, the timing exposure so is very, very critical for certain, for certain health outcomes. So interestingly, some recent studies, including our own studies, found so exposures actually go beyond our own experience. So some studies they found so our parental SES, social economic status, play a very important role in their children's health at late life stage. So this figure is taken from our recently accepted paper by Circulating Research. So it will be appear next month. So this figure shows, the principles of export assessment in my field. So basically, export assessment includes two key components: human activity pattern and locations, also called microenvironment. So human activity pattern refers time spent at different locations. Think about us, we're moving every day, from our home to office, classroom, restaurant, shopping mall. We spend different amount of time at different locations, and what we were doing at each location. Sleeping, sit, standing, walking, and running. So let me use air pollution as one example, because for air pollution, so one parameter is inhalation rate. So different activities lead to different inhalation rate. And also, at different locations, the pollution levels could be very different. So we can think about if you live in the downtown area, or maybe next to freeway, or next to a park, or maybe next to the chemical plant. So the pollution levels could be very different. So as shown in this figure. So even with one city, we can see a large gradient of urban air pollution. So ideally, we want to measure all those parameters: pollution concentrations at different locations, time spent at different locations, and inhalation rate. So this is the ideal scenario. So in most situations, so we don't have direct exposure measurements, especially for retrospective studies. So the question is, how can we assess exposure? So let me use air pollution as example again. So this slide shows evolution of air pollution exposure assessment method since 1990s. From citywide averaging to nearest monitor, inverse distance weighting, kriging, to even advanced methods, land use regression, AOD-based models, machine learning, deep learning, and AI. So here I just want to emphasize one point. Some methods are heavily influenced by the geography field, especially, for example, like kriging, land use regression, and AOD methods. So basically, some methods, originally the idea actually originally are from geography field. For example, kriging, land use regression. We just, tailor this method, for the context of environmental exposure assessment. So I'll go through this method, quickly. So this map shows, the city of Mexico. Here we see lots of dots, the black dots. So every dot represents an individual. So you also see a lot of red triangles. So they are basically the air pollution monitors. So the question is, how can we assign exposure to air pollution for every individual in the city of Mexico? So if we use, the citywide averaging method, so basically we take the average of concentrations across all monitors in the city of Mexico. So then we assign this, we assign these values to every individual, to all of those, dots living in the city of Mexico. So this method is very simple, but it doesn't generate, spatial variation. So basically, for all the people living in the same city, they will have the same exposure. So actually, in early days, like the 1990s, a lot of, some of the landmark studies have used this method. For example, like the Harvard 6-city study. So which is a landmark study to promote, to add PM25 into a national standard in the US. Because at that time, EP didn't have the regulatory monitor for PM25. So even nowadays, sometimes we still use this method. For example, for some of the metals, we don't have a lot of monitors to monitor, the metals. So next one, is the nearest monitor. For example, if we look at, this, maybe this person, this guy here, right? We just find out, which monitor is nearest to this person address. Then we send the concentration from this monitor as an exposure to this person. So this we add some of the variation to the exposure, but it doesn't account for the nearby other monitor information. So that's why we introduce like the kriging. So basically we use the kriging to interpolate exposures for every individual, based on information from all monitors. So those three methods are very popular in 1990s and before the 2005. So the problem is that so those three methods only consider pollution concentrations only. So they don't account for other information. So for a lot of environmental studies, so they focus on urban air pollution and urban populations. So we need, the better method to characterize, the spatial variation of urban air pollution. Because, for example, like the PM25, so even in some of the big cities, they usually only have like 10, around 10 monitors. From those metro, for those mega cities, they have more than 10 million population. 10 monitors are not enough to generate the fine scale exposure. So now let's look at next one, the land use regression. So what's the land use regression? So basically it's a linear regression with a lot of GS derived land use variables. So actually this idea was proposed by folks in the geography field 15 years ago. So here I just use this as a MESA course study example to explain this method. So this work is to characterize the PM 10 to 2.5. So basically the coarse PM, coarse particles. So why study PM coarse? So if we look at the national air quality standard, so it does include PM10 and PM25, but it does not include PM coarse 10 to 2.5. Should we regulate PM 10 to 2.5? So actually this is a question from EPA. So that's why EPA found a bunch of studies to study the health effects of PM coarse. So this project is in collaboration with MESA and MESA Air, which is investigating the impact of PM on the progression of atherosclerosis in 6 cities in the US: Los Angeles, St. Paul, Chicago, Winston-Salem, Baltimore, and New York City. So this project is funded to add detailed characterization of PM coarse in 3 cities: St. Paul, Chicago, and Winston-Salem. So MESA is a population-based cohort study in the US. It includes 6,000 participants in 6 cities. So roughly like 1,000 participants per city. So now, MESA study actually is a kind of landmark study in environmental health field. So in this study, we collected PM10 and PM2.5 samples simultaneously. So for every city, so we collect samples over a 2-week period in summer and winter to account for seasonal difference. So the uniqueness of this study is we collect samples simultaneously at about 40 locations in every city per season. This is probably because at that time we leverage the MESA Air study. So MESA Air study is the largest funded study by EPA. So that's why we have a lot of instruments, because if you want to collect samples simultaneously, you need a lot of instruments. They are very expensive. So that's kind of uniqueness of this study. So we analyze the total mass and concentration and species. So for this study, we only choose the PM cores total mass and 4 species. We choose copper and zinc, which are indicator of brick and tire wear, silicon and phosphorus, which are indicators of soil and agriculture. Because different species reflect different sources. So if we have better understanding of sources, it's better for EPA and the local government to regulate those sources. So this slide shows the categories of land use used in this study. For example, commercial land use, residential land use, transportation, population density, emissions, elevation, imperviousness, and NDVI. For example, for transportation, we calculate the distance to nearby freeway and major road. We also calculate, the road density within different buffer, as shown here. For example, 50-meter buffer, 100-meter buffer, until 5,000-meter buffer. So why calculating so many buffers? Because we don't know which buffer is the best. Because all those buffers are kind of proxy of emissions. So now we have a total of more than 800 variables. So we only have 40 samples per season per city. So this is a typical high dimension problem. So we follow this, this modeling procedure, to build our models. First, we screen variables based on, their correlation and spatial variation. For example, for some variables, if they don't have the strong spatial variation, we just delete those variables. For some variables, for some variables with different buffers, so we just pick up the best buffer based on correlation between buffer variables and the PM cores concentrations, because all those buffer variables are highly correlated. Then we use lasso, the least absolute shrinkage and selection operator, a method to further narrow down variables to 15 variables. So lasso was a breakthrough technique, statistical method in I think around 2005. So it is very popular in the high dimension studies, especially in the biostatistics. So after we reduce the number of variables to the 15 variables, so finally we conduct an exhaustive search to examine all possible combination of variables. We do add one restriction to because we want our models as concise as possible. So that's why we will have the limit. We limit covers, I mean, up to the 6 variables. So this slide shows our model results. So basically, I mean, we try the 2 methods, one the land use regression, another universal kriging. So basically, land use regression is just a linear regression. For universal kriging, we use, I mean, we use universal kriging to account for spatial correlation. So if you look at the results from 2 methods, they're almost identical. So basically, I mean, universal kriging doesn't provide additional spatial information, besides those spatially correlated variables. Because I mean, for the land use regression, most of those land use variables are spatially, provide spatial information. And also the model performance vary by city. We see the best, I mean, the prediction in Chicago, followed by St. Paul and Winston-Salem. So why the model performance is kind of low in Winston-Salem? Probably due to, I mean, the less spatial variation of our collected samples in Winston-Salem. So here we also see, the model performance vary by, species. So here is our final product. So if you look at the background map, so basically we use our prediction model to generate, I mean, prediction at a fine, grade in 3 cities. So here you also see a lot of, I mean, the black dots. So basically they are the MESA participants. You see here like the square, diamond, and circles. So basically they are the sampling locations. For some locations, we only collect sample either in summer or winter. For some locations, we collected samples in both seasons. So this paper was published in Environmental Health Perspective. So if you're interested in the details, you can refer to this paper. So this method, I mean, it is very nice, but the drawback is very, very expensive because you have to conduct a field campaign. You have to deploy all instruments, a lot of logistic issues. So then we use, I mean, the recent, I mean, we use, I mean, the certain information to develop models to predict, I mean, ground PM 2.5. So here's just one example. Because, I mean, the satellite-based AOD also optical depth, so which is a measure of light, which is a measure of the scattering and absorption of light by particle in a vertical volume of air. So basically, the AOD is the proxy of ground PM concentration. But however, so the relationship between AOD and ground PM 2.5 concentrations vary temporally and geographically. So basically, this relationship is dynamic. So if you look at, I mean, today, this month, last year, even in the same region, so their coefficients are different. And also, if you look at different region, their coefficients are also different. So that's why, in order to use AOD, for environmental studies, we need to calibrate. So that's why we developed model to predict the ground level PM 2.5 concentration using satellite AOD. Here we have done one study in Beijing in 2015. So at that time, I mean, we provide, I mean, the finds, I mean, the PM 2.5 prediction in Beijing. So that's why it was selected as a feature article of Environmental Science and Technology. So I think almost everyone, use the Google Street View to some degree, right? So this is a Google Street View car. So this is the camera. So we have done a cool project. So basically, we put in some air pollution instruments inside this car. So when this car, goes out, when it's taking the pictures, it can also automatically measure air pollution concentrations. Because this car, went through a city, at many stops. For example, like this, make a lot of stops, taking a lot of pictures. So for example, in Houston, so this study was done in Houston. So we have the air pollution measurement at more than 10,000 stops, 10,000 locations. So if you go back and look at this one, so for this one, we only have the 80 locations per city, 40 locations per season per city. But here, we have more than 10,000 locations and location-based air pollution measurement. So, because for urban environmental health studies, we need a very fine scale exposure assessment. So those information, like more than 10,000 locations, can provide a huge information for our exposure models. So in this work, we leverage this big data and also the AI, machine learning method. We use extreme gradient boosting in this study. So XGBoost, is a very popular algorithm that have been dominating in applied machine learning in recent years. So basically, it's a decision tree method. So decision tree is an algorithm to predict, the outcome or dependent variable by evaluating a series of the if, then, else, true, false questions. So the gradient boosting, started to make the prediction based on the raw data of the samples. For the next decision tree, it's built on the residual from the first tree. That's why we call gradient boosting, and so on and so forth. So finally, the gradient boosting method will make the decision based on all those trees. It's kind of a kind of ensemble method. So this slide shows the model performance based on the cross validation. So basically, for particle number concentration, nitrogen dioxide, NO, and also the black carbon. So the R square, the cross validated R square, is values are either beyond 0.9 or close the 0.9. Here 0.87. For the PM2.5, so the R square from cross validation is 0.77. So basically, all those models perform very well, especially for those four the pollutants. So here we just use those prediction models to make prediction at a very fine scale, like the 1 kilometer scale in the entire Houston. So in March 2019, a massive chemical fire broke out in Pasadena, Houston. So about a dozen of chemical tanks were involved. So this chemical fire released about 20 million gallons of waste. So right after this, chemical fire, we set up a low-cost sensor network in Houston. So here you can see those circles. Basically, they are the sensors from our low-cost sensor network. So their concentrations are colored. Light purple means a lower concentration. Dark purple color means a higher concentration. So the background are environmental justice index. So basically, the red color means like the more disadvantaged neighborhoods. So here, we can see, so this this chemical fire affects air quality, especially air quality in those more disadvantaged neighborhoods. So now let's move to extreme weather. So let's start with the question: how hot is too hot? So if you're from North, for example, Chicago, Boston, New York, or if you're from Phoenix, Houston, you probably give me a different answer. So our perception to heat actually depends on many weather parameters. So traditionally, a lot of studies only includes both temperature and relative humidity into the models. Because a lot of weather parameters are highly correlated, so we just cannot, add too many weather parameters into our model. So we have done an interesting study. So we use a machine learning method random forest to include all those weather parameters into the model, to look at which weather parameters are more important in predicting heat-related mortality. So one interesting finding is that we found absolute humidity is more important than relative humidity in predicting heat-related mortality. So this is a very interesting finding. So later on, we also apply this idea to the COVID transmission, how weather affects COVID transmission. So this study have been done a while ago. So this paper published in 2014. So actually, is one of the earliest paper in my field that apply machine learning in the temperature IP studies. So those are our papers, yeah. So I think most of us, check weather forecast very often every day. So question is, do you know how weather forecast is generated? So this figure, so actually, the weather forecast is art and science. So we have done a CDC project, before. So basically, so here, here's the National Weather Service Office. So those are forecast guys. So they collect information from weather station, balloon, satellite, radar, and a lot of numerical models. So here's a question. Because we have so many numerical models, so different model will give you different forecasts tomorrow or next few days. For the warnings, for example, for the heat warnings, or maybe hurricane warnings, so they have a huge consequence, for government agencies and societies. So they just cannot issue too many warnings, because otherwise nobody believe you. So in this project, we look at how weather forecast uncertainty affects the heat warnings. So this paper was published in Environmental Health Perspective. So we enjoy fresh vegetable and fruits every day. But what do we know about this population, agriculture workers? So probably, so actually, I have a few funded projects on this population. So why working on this project, I found, for those guys, so that they don't have the monthly or weekly stipend. For most of those guys, their salary is piece rate. What does this mean? So basically, their salary is based on their production of goods, like the vegetables, fruits. So that means they have to work very hard in order to get more money. So basically, in the summer, for most of us, we can stay in the indoors, right, with air conditioning. But for this population, they have to work outside, and they have to work very, very hard. And also, this is a very vulnerable population, because most of them live, are poor. Most of them do not have insurance. So that's why the heat is a big issue for this population. So we have done a very interesting study using so this is a pill. So actually, this is a sensor, temperature sensor. So they can each ingest these sensors into their body. Then we have the wireless receiver. We can receive their core body temperature information, because the core body temperature is very critical for everyone's health. It's much more accurate than the outdoor, like the ambient temperature. So we also have done some projects on built environment and health. So in the US, there's one significant public health issue is obesity among Mexican Americans, because the prevalence of obesity in this population is much higher than nation average. So we look at the cohort, Mexican American cohort in Houston. So here you see a lot of dots. So basically, they are the cohort participants. So we look at their neighborhood environment, for example, traffic air pollution, built environment, food environment, and green space. How those factors affect the obesity and obesity related biomarkers, for example, like the telomere length and the mitochondrial DNA copy number. So epigenetic aging and epigenetic clock are novel biological age indicator. So they are calculated based on statistical models, based on a set of molecular biomarkers, for example, DNA methylation. So the biological age indicator represents individuals' physiological state and overall health. So the differences between chronological age and biological age indicate accelerated or decelerated aging process. So this figure shows, a lot of diseases and risk factors, BMI, and also the lifestyle factors associated with, epigenetic aging. So recently we have done a very interesting study. So we look at, green space, how green space affects epigenetic aging. So basically, we look at a cohort study in four cities in the US. We look at their exposure to green space since early adulthood to middle adulthood. So we found a greater exposure to green space is associated with slower aging, epigenetic aging. So, and also we found, we look at the neighborhoods. We found for those, more disadvantaged neighborhoods. So the association between green space and epigenetic aging is stronger. So which have some implication for urban planning. So which means, if you plan a park in a more disadvantaged neighborhood compared to a more, well-maintained neighborhood, you probably will get, more benefits. So here just give example about exposure to social determinants. So the heart diseases are #1 cause in the US, #1 cause of mortality in the US. So in this study, we look at how social determinants affects healthcare cost. So I think the interesting idea here is that we use healthcare costs instead of diseases. Because the healthcare cost money reflects severity of diseases. So I'll go through this study very quickly. So we look at three healthcare cost indicators: total healthcare cost, inpatient and outpatient the cost. Here we can see if we use different indicator, they show different spatial pattern. Here I just we still use extreme gradient boosting method for this study. Here I just want to show some interesting findings. So for relatively disadvantaged counties, like the rural counties, high segregation counties, or poor counties, so the poverty and income inequity are more important in shaping the total care cost of CVD. For the mature counties, counties with low segregation, so smoking and physical inactivity, those behavior factors are more important. So yeah, this is our published paper. So the last one, I just want to talk about urban exposome and social determinants and CVD. So basically, now I have two ongoing projects. One's how urban exposome affects progression of CVD. Another R1 project is how life course social determinants affects progression of CVD. So basically, exposome is a new idea in my field. So basically, it's a combination of natural environment, built environment, and social environment. Because in reality, we're being exposed to many factors simultaneously. So here, just give you example. So this the external exposome we calculate for Chicago, based on our cohort population. We have the tons of the environmental factors. So finally, I'd like to thank my collaborators and students, and also the funding agencies. Yeah, thank you very much. Yeah.
Thank you, Dr. Zhang. So let's look at the QA. So for the participants, if you have any questions for Dr. Zhang, please feel free to post your questions in the QA. So in the meanwhile, we're waiting for other people's questions, and I have some questions. Thank you so much for the excellent lecture, and it's really interesting. So in several of your case studies, you mentioned about a scale, spatial scale. So for example, for the creaking, you divide into different zones. Of course, you have also like individual points, and also you had this sensor based, like you collect the pollution at different locations, and you also had the pill. That was really cool. So you had this pill that the people can eat. And so anyway, so most of your case studies are related to the spatial analysis, that the spatial scale is important. So how do you define the spatial scale in this case to measure the environmental pollution exposure? Do you have, could you just elaborate this a little bit?
So this, I mean, the fantastic question. We actually, I mean, we don't have the unified, I mean, definition of spatial scale, because it really depends on which health outcome you want to look at, and also the which, I mean, pollutant you want to look at. So for example, you know, nowadays, I mean, a lot of, I mean, satellite-based models, right? Usually they can provide, I mean, exposures at concentrations, you know, at 1 kilometer resolution, maybe, you know, 500 meter resolution. So those are great, you know, for most studies. But however, I mean, if you want to look at traffic-related air pollution, that's probably not enough. Because, I mean, the traffic-related air pollution has a very strong spatial gradient. So basically, I mean, the traffic-related air pollution concentrations decrease exponentially with the increased distance to freeway. So for example, usually within like the 150 meters from the freeway, we can see the much higher concentration of NO2. But usually after like the 300 meters or 500 meters, you know, for NO2 concentrations, I mean, usually are very similar to the background concentration. And also nowadays, I mean, I think, I mean, for a lot of studies, I think, I mean, the fine scale, you know, final scale, you know, probably is better. Because, for example, in Houston, we only have about 10 EP monitors for PM2.5. But Houston, you know, is a very large city, right? And also now, I think there's a trend, you know, for community engaged research, because air pollution affects, you know, certain communities more than other communities. For example, in Houston, like the East Houston, that's, I mean, the, you know, largest, I mean, petrochemical industry in the US. You know, for those, I mean, for those communities, they want to know their, I mean, you know, the concentration level in their communities, in their neighborhoods. So that's why, you know, why now the low-cost sensors are getting more popular. Because, I mean, if you have the money, you know, the measurement is always good. So models, you know, all models wrong, but some are useful, right? So ideally, you want to have the measurement, especially if you want to influence the policymakers, because, I mean, they, you know, usually trust more on the measurement, not the predictions. Because, I mean, if you try different models, you may get different predictions. You know, which one should you trust? Yeah, I actually have a conversation with a EP administrator a long time ago, who retired from EP agency, but she told us, I mean, she all want to see the measurement, because that's the truth.
Absolutely. So it
Yeah,
depends on the application, the data availability, and also funding, right? The money to include in the census.
Yeah, so that's why because the measurement, especially the measurement of the species like the metals, in PM, those are very, very expensive. You just cannot get enough of those measurements. So that's why it's a trade-off.
Right. Yeah. Okay, now we got quite many questions. Okay, so first, how can I learn AOD analysis? Is there any online workshop available for that?
So AOD analysis, I think this is probably a good question for people in remote sensing field. I remember there's some workshops in the conferences I usually go. Sometimes they offer AOD workshop. Because for AOD, I think the one, but nowadays, the processing data is much easier than the early days. Because if you want to derive the AOD based on the raw data, it will take a lot of time and also require strong expertise. But nowadays, so I think yeah. So my answer is that there's some the workshop. Probably you want to check the different conferences, and also actually there are also some the open data sites. So actually you don't have to do the AOD analysis yourself. They already provide the model prediction at the census tract level. So because nowadays in my field, so AOD model is great, but ideally you want to use a hybrid model. What does that mean? Want to integrate information from satellite, ground land use, emissions, traffic, and also from the atmospheric air quality models. Because each data source have their strengths and weakness. So now there's some already, the validated model, they provide prediction from those hybrid models. Maybe you can send me, the emails after the seminar. I can share some of the links. Yeah.
Yeah, please feel free to contact Dr. Zhang. So the next question, what are the biggest challenges for assessing the relationships between environment and urban health?
Oh, this is a very broad question. I would think, the one thing is about exposome, because, we're, in the real world, we're being exposed to, many factors simultaneously. So, for a lot of traditionally, you only look at, one pollutant or maybe few pollutants together. But now I think, it's a trend to look at, multiple factors together. And also nowadays, I think another trend is that social determinants is becoming more and more important. So as a slide, I showed in my presentation. So for example, the association between environmental factors and the human health are always, often modified by social determinants, at both individual level and the neighborhood level. For example, let's assume you want to conduct an innovation study to promote physical activities. So you can try different neighborhoods. So for those like the middle class neighborhood, or maybe the neighborhood with more parks, a green space, or a safe environment, you may get more likely get more success from those neighborhoods compared to those low ICS neighborhoods with less resources and unsafe environment. I think reality, yeah. So I think this, and also another thing I want to say, probably the causal relationship, because most of studies only report association, may or may not causal, right, between the environmental factors to human health. And a lot of open questions we don't know. For example, for a lot of chronic diseases, we don't know biological mechanisms well now.
Okay. So we have about 6 minutes. So maybe we have time for 1 or 2 questions. So have you tried the geographical weighted, I think, regression model or regressions for random forest for air pollution estimation? And also this Nicola also mentioned about the data. It's the European Space Agency based on Sentinel-5 data. Have you tried that data as well?
For the first question, yeah, we did try like the machine learning method, for predicting air pollution and temperature. Maybe I can share that with you later. For the second question, no, unfortunately, no, yeah. But yeah, this is a great question.
Okay. So from Wenwen, could you please also comment on the potential as well as the challenges of incorporating mobile biometrics sensors like GSR sensors, eye trackers, glass heart rate monitors into the studies?
This is also a great question. So I think this is the trend because now, because the smartphone, we can attach a lot of sensors to the smartphone. I think it's getting more and more popular. So, and also this will be, this also, a great, opportunities for the researcher because you can get a lot more information, actually the big data, from those sensors, like the heart rate, the Fitbit, those kind of sensors, yeah.
Okay, next question from Xue. Thank you for the presentation. I wonder how will you measure the time lag of environmental effects on health? For example, it may take years for people who exposed to air pollution. That's a good question, yeah.
Yeah, this is also the excellent question because we don't have the, so usually, in my field, we usually say like the short-term exposure or long-term exposure, but there's no unified definition of short-term exposure or long-term exposure. For example, for cancer, the probably takes, like the 10, 20, 30, 40 years to develop the cancer. So I think this question is great. It really depends on which health outcome we want to look at. For example, like the asthma exacerbation, usually, for example, for someone, if today air pollution ozone level is very high, someone may go to the hospital, today, or maybe tomorrow, right? Because this will be a short-term exposure. For long-term exposure, like for lots of chronic diseases, like the cardiovascular diseases, maybe the developmental asthma, or maybe the cancer, they will take, years of time. So this, it also like the very important, the topic in my field, because we don't have the unified definition of long-term exposure. So that's why we will try some of the sensitivity analysis. So, you could try, 5-year, 10-year, 20-year, but still it's very challenging for the cancer because, the latency period could be very, very long,
Okay, thank you. So please share the mail ID of the respective speakers. So if you can. Let's thank you again, Dr. Zhang, for your excellent presentation and lectures. And thank you for the participants for your time. Have a great, I don't know where you are from, Europe or the US, but anyway, enjoy your summer and see you in our next webinar. Thank you.
Yeah, thank you very much. Okay.